All right, so we are going to continue on with part 2 of lesson 3.2. We are looking at applying the properties of radicals and rational exponents. Example 4 has us adding and subtracting like radicals and roots. When we subtract, add and subtract, just like with variables, they have to be exactly the same. So example A, we have the fourth root of 162 minus the fourth root of 32. Now because they're both fourth roots, it's very tempting to say, oh, they're already like terms, but they're not. They have to be alike on the inside. So let's take 162, and we're going to go ahead and break that apart. So I'm going to take the fourth root of 81 times the fourth root of 2. So if I combine them, it equals 162. Separated, it's the fourth root of 81 times the fourth root of 2. And then I'm going to do the same thing to 32. Let's divide that by 2. So I get the fourth root of 16 times the fourth root of 2. So now we see I have the fourth root of 2 on here. That's like saying a or x or some other common variable. These are common factors. So I'm going to take that out and we'll put that at the front and we'll have the fourth root of 81 on the inside times, or sorry, not times, subtracting the fourth root of 16 over here. Now we want to go ahead and simplify this a little bit further inside. 81, if we do the prime factorization of it, it's 3 times 3 times 3 times 3. Well, it's fourth root, so we want 4 3's. So the fourth root of 81 is 3. And for 16, if we do the prime factorization, it's 2 times 2 times 2 times 2. So again, 4 2's. So we're going to simplify that. And so now we have 3 minus 2, which equals 1. So 1 times the fourth root of 2. All of this is going to simplify to just the fourth root of 2 as our final answer. All right, so it takes a little bit of time, a few steps to get there to simplify it, but once you do, now this is a much easier problem for us to solve than trying to go from the very beginning. For part B, it's a little bit easier. Same thing we want to do with radicals, our rational exponents. We want to make sure that the base and the exponent is exactly the same. Because this is the same thing as saying the square root of 7 to the third. So we want to make sure that what we see here is exactly the same base and exponent. So 7 to the 3 halves is 1. 1 times 7 to the 3 halves plus 4 times 7 to the 3 halves. So I can add 1 plus 4 and multiply that by 7 to the 3 halves. And so this will be 5 times 7 to the 3 halves. And that's our simplified answer until I needed to go as far as actually getting the calculator out and solving it. But remember, when we simplify, we're looking for exact answers, and if we need to use the calculator at any point, it's going to give us a decimal, a rounded answer. We don't want that yet. All right, so let's clear this off and move on to our next slide. All right, example 5. We are going to be simplifying expressions involving variables. So not only are we concerned about the roots and whatnot being similar, but we also want to make sure the variables are similar. All right, so let's take a look at example A. We have the cube root of 8 times y to the 6th over z to the 12th. Now, I'm going to go ahead and split this up into 2 parts. And let's do the cube root of 8 to the y6th over the cube root of z to the 12th. Now I'm going to do the top part, the numerator part, separately using the old school way and talk you through an idea that helps simplify it. Again, using prime factorization, I can go ahead and simplify everything. 8 is 2 times 2 times 2, and y to the 6th, of course, is y times y times y times y times y times y. We want cube roots, and so we're looking for 3's. So we have 3 2's there, 3 y's here, and 3 y's here. So we can bring those out, so we have 2 times y, which gives us y squared. Now also remember that we could rewrite this. So I'm going to do this for the denominator to show you another way of rewriting this. I could say that this is the same thing as z to the 12 over 3. Remember, if I have a variable being raised to a rational exponent, I can rewrite that in radical form, where the denominator is the root, the nth root, and then whatever the numerator was is the exponent on the inside. So I'm just going the other way around. Because now I have z, 12 divided by 3 is simplified to z to the 4th, which is a whole number, which means it's not a radical. So my final answer is 2y squared over z to the 4th. I could have taken the z's apart and said z times z times z times z and so on and so forth until I had 12 z's out, and then grouped them by 3's, and I would have had 4 groups of z. So z to the 4th. I'm just simplifying that step. I'm going to go ahead and erase this so we have some room for part B. All right, so part B, we have the cube root of a squared over b. So again, let's go ahead and separate this. So we have a squared, cube root of that, and the cube root of b. Now, we already know that we need to get rid of that radical sign. We can't have a radical sign in the denominator, nor can we have a fraction inside a radical sign. So I need to think to myself, okay, what do I need to have in order to get rid of the radical sign? Well, I would need to have 3 b's. So I only have 1, so I need 2 more. So b times b is b squared. So I need to multiply the denominator by the cube root of b squared so I can get my 3 b's. But of course, whatever I do to the denominator, I have to do to the numerator to keep it equivalent. So let's go ahead and combine that. I have a squared times b squared up in the numerator, and then I have b to the 3rd power of the denominator, which means the cube root of b to the 3rd power, of course, is b. Now you may be saying to yourself, oh, that doesn't look any simpler. Looks like it was easy enough to begin with. But, again, the rules of simplification mean we cannot have rational numbers, fractions inside of a radical, and we can't have radicals in the denominator. So it doesn't look necessarily any simpler, but it honestly would be if I had a longer, more complicated problem. All right, let's take a look at our last example. Perhaps if I make this into a mouse. There we go. Example 6, we are going to be adding and subtracting expressions involving variables. So very similarly to what we just did in example 4, but this time we also have variables included. So here we have the same root. We have the square root of k minus something times the square root of k. So let's take out the square root of k, and we can simplify 4 minus 5, which would give us the square root of k times -9. But remember, when we rewrite this, we always want to put the radical last. So -9 times the square root of k. Easy enough. All right, taking a look at part B. I'm going to go ahead and change my pen here for a second because it's going to make it easier to see what's going on. But notice that a to the 1/3 times b and a to the 1/3 times b is repeated. That's our common factor. So we want to go ahead and take that out and subtract what's left over. So 9 minus 2 is 7. Again, writing this in proper order, we put the coefficient first, And then we put our variables in alphabetical order. And there we go. As easy as that. Now the next slide is going to be talking about all the different sample problems that I have for you. So if you don't feel comfortable with those yet, go back, review some of these examples, and then move on to the sample problems. Practice these on your own. So there are 6 questions. These are from all 6 lessons. So you may have to go back to part 1 if you need to. Pause this, answer these questions at your own pace. Make sure you show your steps and your work. And then when you're ready, go ahead and move on to the answer slide. All right, so hopefully your answers match the correct answers shown here. If not, again, circle those, and in class we will discuss the proper procedures to go through them, and then you can also work in your partners to get the correct answers as well.